In this video, I'm going to start on a series of videos. So the next several videos after this one are going to be about reactions of alkenes, which, remember, alkenes are these hydrocarbons that have double bonds in it. So we end up with these pi bonds. So we have the density above and below the sigma bond here, giving us the pi bond. And so because these electrons in the pi bond are held more loosely than the sigma bonds, we can there is some reactivity that we can get from these pi bonds here, and so that makes this sort of a functional group that can perform and engage in chemical reactions. And so there are three essentially schema for types of reactions. The two that we've discussed already so far are the elimination and the substitution, where the elimination we are bringing in this saturated alkane here, and we're going to remove these two groups right here so that we end up with an alkene and the groups that left right here. With the substitution, we have the saturated alkane here. And so we're going to replace one group with another group. So one of them is the nucleophile here, and the other one is the leaving group. And so we replace those with each other here. So the first one, if you're thinking about it in general chemistry terms, is sort of a decomposition reaction, where the second one is a single displacement reaction. But the ones we're going to be talking about in these alkene videos are addition reactions. And so we start with our alkene here, we bring in these two groups, and then we add those to our alkene to get rid of that double bond and put these two groups onto this and form an alkane. And so some reagents will react with the carbon-carbon double bond with the help of a catalyst. So, for instance, when we do the hydrogenation here, say of ethene to make ethane, by adding these hydrogens here, we need a platinum, palladium, or nickel catalyst here in order for this to occur. Other reagents do not require a catalyst, and strong electrophiles can pull the delocalized pi bond, which is further away from the nuclei and held more loosely, to form a new bond here. And so that kind of looks like this, where we have our alkene right here with our pi bond there, this electrophile, which is represented by this E plus here. It doesn't necessarily have to be positively charged, but it's just showing that the electrophile is going to at least have a partial positive. So it's going to attract these electrons. So we end up with, I guess you could say, kind of a transition state that looks like this. So we end up with a partial positive here, and this is going to bond up to our electrophile, and so all of the electrons in the pi bonds will end up in the in this new sp3 hybridized orbital here, bonding to our electrophile, and then we end up with this vacant p orbital here, so we end up with a carbocation here. And that's actually going to be important that we're forming this carbocation, because that's going to inform sort of how these things actually bond to it, so whether it's bonding to the more or less substituted thing, and what is called Markovnikov's rule that we'll get to here in a little bit. And so yeah, the general scheme for this, we have our alkene here, our electrophile. The electrophile bonds to one of the carbons here. We end up with a carbocation. Then a nucleophile comes in, and it's going to bond to this carbon right here. And so we end up with our product that looks like this. So we have our electrophile bound to one carbon, and then our nucleophile here bound to the neighboring carbon. And so we can look at that here in a somewhat more concrete example. So we have this this 2-butene here, and so the electrons from this double bond, sometimes you'll see people go like that, sort of putting it over to that one carbon to show that the hydrogen is going to bond to that carbon there. The electrons will go to this bromine here, so we end up with this This hydrogen is now bound to that carbon. We've produced this this nucleophile with the bromine here, so that's going to quickly go onto that carbocation there, and so we end up putting this hydrogen and this bromine onto here and forming butane. All right, and so here I'm just going to go through some of the types of reactions that we're going to see in this and the next several videos. And so these are all just different kinds of addition reactions to alkanes. And so we can do what's called hydration, where we're putting this water on. So we see that one of the hydrogens ends up here, and then the remaining OH ends up right here. So the hydrogen is the electrophile that ends up on one carbon, and then the OH is the nucleophile that ends up in the other carbon. We'll have hydrogenation, which is when we're just putting two hydrogens on here, so we're just adding the hydrogens on the two different carbons in that alkene there. We can do hydroxylation, so we'll use this hydrogen peroxide here, and we'll end up with these two alcohol groups on here on neighboring carbons. We can also do oxidative cleavage, so we use O2 here, and we take the carbons with this double bond here, and we split them apart, putting oxygens on there, resulting in two carbonyl species here. We will also have epoxidation, so we're going to use this peroxy acid. So this is sort of like a carboxylic acid, but instead we have two oxygens here, and so we're going to end up with this epoxide group right here. And so that is just adding one of the oxygens across that double bond there. Then we'll see halogenation, so we just put a halogen here, so it could be, Cl2, Br2, I2, anything like that, and we're going to add those across that double bond like this. Then we can do halohydrin formation, so we're putting a halogen on one of the carbons and a alcohol group on the other carbon like that. We can also do hydrohalogenation, so we put in something like HCl or HBr or HI, and so we're going to add a hydrogen on one of the carbons and then the halogen on the other carbon. And we can also use a carbene here. So remember, a carbene was something that looked like this. So it's a carbon, it has two R groups, or it could be two hydrogens, and then it has a lone pair like that. So it's an uncharged carbon, but these are extremely reactive because they don't have a full octet. But we can use that to put a propane group across the double bond here, so a 3-carbon ring across that double bond there. So that's why it's called cyclopropanation. And so those are the reactions that we're going to be looking at in more detail across the next several videos here. But there is this important thing that I hinted at earlier that I need to introduce, which is called Markovnikov's rule. And this can be stated essentially in two different ways. So the first one is that the addition of a proton acid to the double bond of an alkene results in a product with the acid proton bonded to the carbon atom that already holds the greater number of hydrogen atoms. And so what we mean by that is if we have our alkene here, so we have our alkene right here, like this, and we're adding, say, an HBr here, and we'll say that that this is some R group, this is an H, this is an H, and this is an H. So which of these carbons is the H going to add to? Well, it's going to add to the one that has the least, or the most number of hydrogens on it. So we will end up with something that looks like this. So this will be a positive charge on there with our hydrogens here. So I should actually get rid of this right here because we're forming that single bond. And so then this will have the 3 hydrogens on it, including the one that just added to it. And so we can see the reason why this would be the case because we want to put the carbocation right here on the carbon that's going to be the most stable with a carbocation. And so that's actually sort of the way that we phrase it in the second way of saying Markovnikov's rule. So in an electrophilic addition to an alkene, the electrophile adds in such a way as to generate the most stable intermediate. So the most stable intermediate is going to be the one that has the carbocation and the most substituted carbon right here. So we would rather have a secondary carbocation, for instance, than a primary carbocation. And we would also rather have a tertiary carbocation than a secondary carbocation. And so we're forming that most stable intermediate. So the result is that the electrophile, so in this case the H plus binds to the less substituted carbon, and the associated nucleophile, so the Br minus in this case, binds to the more substituted carbon. And so we can look at it like this. So we have this HBr coming here, and so we could either have this right here, which is our alkene. We could either have the double bond electrons go to the hydrogen here on that carbon, or we could have it go like this onto that carbon and have the electrons go to the Br there. And so in the first case, we're ending up with this carbocation and this tertiary carbon, where in the second case, we're ending up with it on the secondary carbon right here. And so this one up here is going to be the most stable, and so this is going to be our major product right here. So this is going to be the major product right here. And so we see that this one, I put this big X through it because we're not really going to see much at all of that product, because this this intermediate here, the secondary carbocation, is less stable than the tertiary carbocation intermediate. And so seeing the hydrogen go to the carbon with more hydrogens on it is going to be sort of the net result of Markovnikov's rule. So we might even call that the Markovnikov product there. And this will also be the case whether we use iodine or chlorine here. So yeah, whether we're using bromine, iodine, chlorine, we're going to get that Markovnikov product. But of course, this is chemistry, so we can't introduce a rule without almost immediately talking about the exceptions to the rule. And so with a free radical addition, we get the anti-Markovnikov product. And so if we have this peroxide right here, we heat it up so that we form these two free radicals. We have one of the free radicals react with this HBr here, so this will go in here, this will go in here. We form the radical bromine right here. So we see this is exothermic, so that's going to be favorable, at least as far as the heat of the reaction goes. So we have this this radical bromine here. We're going to have this electron come here, this electron come here, and then this one go right here. And so we see we've now added the bromine to the lower substituted carbon, because now we need to get the free radical on the more substituted carbon so that that is actually more stable that way. But right now, what we see is that we're adding the bromine first before we're adding the hydrogen. So the stable carbon is going to be the one that has the hydrogen go to it, because we're adding the bromine first. So the intermediate that gets formed already has the bromine bound to it, rather than having the hydrogen already bound to it. And so yeah, we end up here. So we can have this electron come here, this electron come here, this one go to the bromine. And so now we have formed our anti-Markovnikov product here. And so again, this has a delta H that's negative, and so as far as the heat of the reaction goes, that's going to be favorable there. And so this reversal of orientation in the presence of peroxides is called the peroxide effect. But this only occurs with the addition of HBr. And this is because with HCl, the reaction of the alkyl radical is strongly endothermic, and with HI, the reaction of the iodine atom with the alkene is strongly endothermic. And so we can look at that here. So this reaction of the HCl with the alkyl radical here is going to be the endothermic one. So where we have this coming in here, this going here, and then this going here is going to be strongly endothermic. So we can see that here. And so that's going to be unfavorable. And then with the iodine, so the reaction of the iodine atom with the alkene is going to be strongly endothermic. So having this come here, and then this go there, so that we end up with this right here. So this is going to be unfavorable as far as the heat of a reaction goes there. And so it's only with this HBr that we see this anti-Markovnikov product. But anyway, that was what I wanted to talk about in this video. I think this the main takeaway from this video is this Markovnikov's rule here, because this is going to be important, and of course the Markovnikov rule and the exceptions to the Markovnikov rule are things we're going to be talking about quite a bit throughout these videos on alkene additions. And so that is kind of the main takeaway from this video, this first video in this series of upcoming videos. So yeah, we have these three types of reactions. We're looking at the addition reaction. So we're doing electrophilic addition of alkenes, which is going to be essentially looking like this, where we are going to follow the Markovnikov rule. These are the different kinds of reactions we'll be looking at throughout these videos. The Markovnikov rule says that this hydrogen is going to bind to the least substituted carbon because we want to form this most stable intermediate here, and this will be true with whether we're using bromine, iodine, or chlorine. But well, an example of an anti-Markovnikov rule, and we'll run into other anti-Markovnikov reactions in the upcoming videos as well, is this free radical addition here. And so we call it the Markovnikov rule, but like I said, this is chemistry. So every rule has exceptions to the rule, and so that's sort of the lens in which we will be talking about these reactions in the upcoming videos, is the Markovnikov and anti-Markovnikov products here. But anyway, I don't want to ramble too long. I hope you found this video helpful, and I will see you in the next one.